This is the next big category. The node running on the random access max will send data at the full data rate. And there are no coordinations among nodes. Therefore, when there are multiple senders sending data at the same time, we have collisions. So the key designs in these random access max are often how one detects collisions and how one recovers from the collisions. So these will be the things we talk about in these examples of random access max coming next. Slotted Aloha. This is one of the very early random access max. So in the protocol, all data frames are the same size. The transmission time is divided into equal time slots as well. Each of the time slot is exactly the time to transmit one of these data frames. When nodes get data to send, they will start the transmission right at the beginning of a time slot. Therefore, they will complete transmitting the frame at the end of the time slot. So all nodes are synchronized, of course. Otherwise, they won't know, right, when it's the beginning of a time slot. When two or more nodes transmit at the same time, all nodes will detect the collision. All right. Now, during operation, when a node receives a fresh data frame from above, it would then wait until the beginning of the next slot and then transmit. So, as defined here, a node does not send a frame in the middle of a slot. Now, when the frame is out, the node will be able to detect whether there's no collision or collision. If there's no collision, the node will just keep on sending in the subsequent slot. If there's collision, the node will retransmit, recover from the loss, retransmit the data frame in the subsequent slot, but with the probability. And this is probabilistically tried until it's finally successful. So here's an example of 3 nodes running on a slotted Aloha link over time. So in the first time slot, each of them has data frames to send. So out, 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 and collision detected. So C here indicates a collided slot. Each of them will then try with probability P whether they retransmit. And so in the second time slot, we see randomness decides that none of them transmit. So we ended up having an empty slot. Third slot, 1 and 2 decides to retransmit. Again, collision. So we get a collision slot again. Fourth, finally, 2 is the only one decided to retransmit. So this will come through and we have a success slot. And so randomness will continue to play, and eventually we see node 1 here is the only one transmitting. We get the second success slot. Node 3 is the last one and another success slot. So what's nice about Slotted Aloha is this. One single active node can continue to send at the full transmission rate. It's highly decentralized. All these nodes need to know are just the beginning of time slots. So the mechanism is very simple. On the other hand, we might be wasting slots to collisions and idle slots. For example, these are the collided slots and these are empty slots. These nodes may be able to detect the collision in less time than to transmit the data. So for example, these nodes might detect the collisions right at the beginning. So there's really no need to transmit the rest of the bits in the packets. And clock synchronization is required because each node needs to know exactly the beginning of a time slot. Now let's calculate the efficiency of Slotted Aloha. And here, by efficiency, I meant the fraction of the slots being successful over a long time. Let's suppose we have n nodes with many frames to send, and each would retransmit at the probability P. Now, with those set, the probability of a node being successful in a slot is therefore what? The node hits P and send. The rest of the nodes hits Y minus P and not send. And therefore, the probability of any node is successful is this. Now, to maximize the efficiency, is by finding the p star such that this value is the highest. How do you find p star? You take the derivatives of this term, right? And you set it to 0 and try to find p star. Okay, that gives you the maximum minimum values. So after plugging in the p stars into the formula and take the n to the infinity, meaning there are infinite number of nodes on the Slotted Aloha link, that will give you the extreme efficiency, the asymptotic efficiency, which is 1 over e. So we'll skip the derivation, okay? And that gives us 0.37 utilization of the link.